Welcome back to Math with Micah. This is Micah, and today we are going to be looking at a topic that can often be pretty confusing and kind of tricky, and that is implicit differentiation. Hopefully in this video, I will make light of some topics that have been kind of confusing in the past for many students, and we're going to start by looking actually at the derivative. And this is just a derivative that you probably know by heart and have seen a million times. And it looks something like this. What is the derivative of x in respect to x? And this is, of course, is just 1. But the reason I hate when calculus textbooks have this is because this is what we're actually doing. When we take the derivative of x here in respect to x, what we actually get is a chain rule where we have the derivative of x is 1, and we pick up this derivative of x in respect to x. But of course we see in this case, this is just 1. This is dx over dx, so we just get 1 times 1, which equals 1. And say we had a problem like this, where we're taking the derivative of x, and we're taking maybe, let's say, x to the third. Well, of course, we know this is 3x squared, but we actually pick up, again, we're taking the derivative of this x variable here in respect to x. But again, this just goes away, so we get 3x squared. And that's why when we take the derivative of a variable in respect to the same variable, we never ever write this because we just know this is always 1. But the reason I don't like that sometimes this isn't stressed is because, well, what happens if I'm taking the derivative in respect to a new variable? The inclination might be to say, well, the derivative of x to the third is just 3x squared. But wait, we're taking the derivative in respect to this new variable. So if we had been using this method before, well, we have on the top the variable that we're taking the derivative of, which would be x, but now we have a different variable that we're differentiating in respect to, and that's t. So on the bottom, we have dt instead of dx, and in this case, this doesn't cancel, and this piece right here is very, very valuable. We do not ever want to miss that opportunity to write a dx over dt, because if we write just 1 there, that's going to mess up our whole entire implicit differentiation problem. So let's say we have a little bit more of a complex problem. Let's say we have something like x times y to the third equals 1. And we're told we need to find dy dx. And this is just another way of saying y prime, right? The first derivative. Well, we could, if we want, solve for y here and then take the derivative of y. But what actually is easier is if we do differentiation in respect to both of these variables. So let's implicitly differentiate. And to do that, since we want a dx on the bottom, that means we have to take the derivative in respect to x for the whole entire equation. And we'll go through and do this term by term. So first, for this x times y to the 3, we have 2 separate terms, so we need to use a product rule. So let's take the derivative of x in respect to x, and of course we just get 1, and the dx over dx is going to cancel out, and we leave the y to the third alone. And now we leave the x alone, and we take the derivative of y to the third, and we get 3y squared. But again, we're taking this in respect to x, so what we pick up actually is dy dx, and the derivative of 1 is equal to 0. Now, solving for dy dx, we know this right here is 1, and we can move over our y to the third, so we get x times 3y squared times dy dx equals negative y to the third, and therefore this lets us know that dy dx, which is equal to y prime, the first derivative, that is simply equal to negative y to the third divided by x times 3y squared. In other words, negative y over 3x. And that would be our first derivative in respect to x. Now, you might be asking, how was this ever useful outside of just finding the first derivative? And actually, there's a lot of real-world applications for implicit differentiation. And we're going to take a look at one of those problems right now. And this is a real-world problem that would involve this implicit differentiation. So let's say that we know a tumor is modeled as this spherical shape with radius r, and we know that the radius of the tumor is currently at 0.54 centimeters, and it's increasing at a rate of 0.13 centimeters per month. So what is the corresponding rate of change of volume? So how big is this thing growing in volume per month? So we have our equation v equals 4/3 pi r cubed. And now we're going to start by differentiating this. But the variable we're going to use here is t for time because we want to find the rate of change of volume, but we're talking about time here. So taking the derivative of v, we get 1 times dv dt equals, over here taking the derivative, we get a 4 pi r squared, but again we pick up a dr dt, where this is the rate of change for the radius in time. And now let's plug in all the information that we were given. So if we plug in, we have a 4, we have a pi, we have a 0.54 centimeters, and we have 0.13 centimeters per month. Our final answer for this would be 0.476. And if we want to figure out what our units are for this, we had a centimeters that got squared, and we also had a centimeters per month here. So our centimeters and centimeters squared turns into a centimeters cubed per month. And this makes sense because, again, we're talking about the rate of change of volume, which is centimeters cubed per month, which is our in respect to time. And that is a real world example of implicit differentiation. As always, let me know if you have any questions or concerns about this problem or any topics you'd like to see in the future. And as always, you can email me at mathwithmicah@gmail.com for any concepts you'd love to see on this channel. Take care. Have a good one. Peace.